Okay, so welcome back. It's a pleasure to listen Carsten Schneider. He will speak about summation, theory of difference swing and application. Please.
Okay, so welcome to my talk. I was not sure who is in the audience, so I see some really big shots in symbolic summation and integration, like Aline and Frederick and also Jacques Arthur, and integration summation. So I think it's not a talk directly for them, but it's more for the others who don't know maybe so much about summation theory, in particular in difference rings, and I try to do it slowly. So my talk consists of 3 parts. Today I will talk about the basic summation tools that I have developed in the difference ring setting. And I will focus, so you will see difference rings today, but only in a mild version. Tomorrow I plan then to give more details on the difference ring theory and how this works. So then you see maybe a bit more hardcore difference ring theory. And the last part, I really want to hopefully make a firework of how you can apply the tools for concrete applications. Okay, good. So let's start with the first part. And again, I will start slowly. I will, in the moment, ignore the difference ring theory and just work on the summation tools. And I can do this because I developed in the last years a very careful interface where you hide completely the difference ring theory from the applications. If you want to use my summation tools, you don't see the difference rings. It's all hidden, and I have a nice translation. And in part 2, I will make this more clear how this works. And today you see it only a little bit. So let's start with a concrete example. This actually comes from particle physics. It's a problem from a two-loop massive matrix operator element, so a Feynman diagram. And this was also the first contact when I had with my dear colleagues from DESY, Deutsches Elektronensynchrotron Corporation, and it works now since 15 years, and we had, I think maybe 50 publications in nuclear physics and whatever. So symbolic summation and integration really works wonderfully in the setting, and I will make this clear in the third part. But now let's look at this example. So if you lean back, you see here a summand. And in the following, I denote the harmonic numbers not by h sub n. This is maybe more the combinatorics language or Donald Knuth's language or computer science language. I use here the language s sub 1 of n. This is more the physics notation, but it's very convenient for me later to use it. So whenever you see S1n, it means the nth harmonic numbers. Okay. So now if you look here, you see here the chase harmonic numbers, the k plus chase harmonic numbers, the n plus chase harmonic numbers, and the n plus k plus chase harmonic numbers. And we divide here by factorials. We have here 2 terms, a Friese harmonic sum term and a harmonic sum term. And then we sum this over j and k from 0 to infinity. So in some sense, you have here triple sums. If you would pull this over, you see a sum of sums. And the idea is to simplify that. N is a discrete parameter. It comes from, in the Feynman diagram, it's a Mellin space. In the Mellin space, it's an n variable. That doesn't matter. It's a summation problem, a discrete parameter. And for n equals 1, 2, 3, 4, 5, 6, you can evaluate it. But it's hard work to do this. And if you go to n equals 100, it's very hard work to do it. So I would like to understand what is the value for n equals 1, 2, 3, and simplify it as much as possible. So when I see that, I try first telescoping. This is maybe the first attempt. This is a discrete version of indefinite integration. So let's denote the summand by fj, and by j because j is the first summation variable. I designed the order how I sum in this way. And I ignore the n and the k dependence in the moment. Okay, so I'm given this summand fj, and I'm looking for an expression or a sequence such that this telescoping equation holds. And in this particular instance, I find that expression. It depends again, you see here, on the harmonic numbers and a product, a hypergeometric product. And maybe you have seen that if the harmonic numbers would be gone and there's only one expression, you could have used Gosper, for instance, okay? But here the harmonic numbers are involved, so it's a more general setup. If you don't trust this result, you can plug it in, and then you can use relations such as that S1 of j plus 1, the j plus 1 harmonic numbers are the j's harmonic numbers plus 1 over j plus 1. So you use such relations, you plug it in, and then you do just polynomial arithmetic to see left-hand side equals right-hand side, or left-hand side minus right-hand side equals 0. Okay? And there are no poles, so this is all fine. So we have verified on this level it's correct, and then we can sum this equation over j from 0 to a truncated version. Here on the topmost I have infinity, I go to the truncated version, so it's a finite sum. So by the telescoping trick, on the right-hand side, all terms vanish except at the upper bound plus 1 minus the lower bound. This is now exactly the discrete version of indefinite integration. We plug in the concrete value g that I computed, and I get that result. And finally, I send a to infinity because I want to have the summation for where a goes to infinity. And if we know that the harmonic numbers, yeah. Only the first, this part here. No summation, so I dropped these two summation quantifiers and just look at the, okay.
It's the entire thing or just?
The entire thing. The hypergeometric term plus the hypergeometric term times the linear combination of harmonic numbers. No, it's both, it's the whole thing. Okay. Then I send a to infinity. And I get that result. This can be done with sigma. So I have prepared also, I will do it also online on the computer, but on the slides it's easier to see than if you have a computer algebra system, then it's always harder to follow. So I insert the sum, and now you see it's really the full summand and the truncated version of my summation. There's a comment sigma reduce, which exactly is doing that I do telescoping and do the evaluation upper bound minus lower bound. Okay, we get that expression. And finally, I send a to infinity. I have an extra comment built in, and I get the closed form. So let's do this online. So I load in, the package sigma. I will load also into it the package harmonic sums. I will give a little comment later. This is specialized for dealing with nested sums that arise in physics, which I love to use. And later I use also the package evaluate multisums. But sigma in the moment is the main tool. So I insert the summand. That's the full summand. And then I apply the telescope. So here I define the sum. I have my own sum. This dot means it's not the Mathématiques sum, because when you say Mathématiques sum, it really tries to sum, and then it gives you some stupid functions out, and in worst case, a recurrence or whatever. I don't want this. I want to have my full control of the summation objects. I compute with sigma reduce the closed form. It is. And in the end, I compute the limit. Okay, note that the limit calculation is also done with the computer, so it's also based on computer algebra methods. So let me illustrate that. We can also compute asymptotic expansions for the harmonic numbers, which is a key ingredient to do this limit calculations. So if I type in, for instance, the command S expansion, one moment, of the harmonic numbers, with respect to n, and we compute, say, up to order 6, then we get that expansion. Note that lg of n is my log function, which means this is a log of n plus Euler's gamma constant. So I don't want to pop up that the Euler gamma constant pops up all the time, and therefore we have encoded it by my log. This is log of n plus Euler's gamma constant. And plugging in this expansion into the concrete calculations, will allow us then to compute the limit completely automatically and rigorously. And just to demonstrate the flexibility of this comment implemented in harmonic sums, let me show you another object. For instance, a more complicated sum is like that. One moment. It's a three-nested sum, a sum of a sum of a sum, weights are power 3, 2, 1, and if you send n to infinity, you get basically back multiple zeta values. And if I insert now this sum, m3, 2, 1, and compute the expansion, then I get completely automatically again an expansion where you see, for instance, zeta 2, zeta 3, and zeta 3 squared, where zeta is the Riemann zeta function. And using this toolbox in combination with symbolic summation, we have a full computer algebra machinery in order to deal with infinite sums where we need the analysis calculations in the background. Okay, this was that example, and we obtained that simplification. Now let's turn to the next summation, and so I sum over the next sum. K goes from 1 to infinity, and there's a subtle point here at k equals 0. I have a pole, so I have to be careful. I can only start k equals 1 on. K equals 0, I have to deal separately, and exactly here extra zeta values normally pop up at the borders. This is typical. Okay, so k equals 1, I sum over that, and I want to deal that. So let's try the same thing. Let's denote the summand by fk. I ignore, and it's because of the next summation variable, and I try to solve the telescoping problem. Same trick. This time, no solution. There might be different choices now I could follow. Here I will use the fact that the sum depends also on the discrete parameter n. I haven't used. So let's just say, okay, the f depends also on n, and the g that I'm looking for also depends on n. So use this information if possible. And now I apply basically creative telescoping introduced by Doron and Zeilberger. I take basically the summand, and I take the summand where I replace n by n plus 1. Okay? And then I ask, maybe I find now a telescoping solution if I take the summand, and I take the summand where I replace n by n plus 1 and look for a linear combination of the two guys. This increases the chance. And C0 and C1, the linear combinations, the factors, should be free of k. If they depend on k, it's trivial to get a linear combination. It should be free of k. Okay? I try to find a solution, and here it is. C0 is a polynomial in n, it's minus n. C1 is n plus 2. And g is now again a linear combination of harmonic numbers divided by this. If you don't trust, you can plug in this again into this equation, use relations just like that, and you can verify it's correct. Okay?
Sorry.
Yeah?
Where do you want your g inter to be?
Sorry?
Where does g inter belongs to?
That's a question. So, of course, I will make this clear later, but Gn depends, of course, on the input. So I take the summand object, so the harmonic numbers are in, and these are basically given as granted because I have to represent my summand here in a certain ring or field. So they are given, but it might be that it's good to look for an extension to find something. So I can also extend, but just a warning, the telescoping problem can be easily solved by taking the input sum as a solution. So if you insert something, that is, you get a trivial solution back. So one has to be careful. If you extend, the result should be simpler than the input. That's a simplification. It's an important issue. So, okay, we find that solution, we verify it, and now we sum over k from 1 to a. Then on the left-hand side, we get just again the telescoping trick. Everything vanishes except the upper bound plus 1 minus the lower bound. And on the right-hand side, you get this fancy sum. This looks ugly, right? It's an ugly right-hand side, an ugly sum. Now, but I use the linearity. I can split the two sums into two parts. And now the crucial thing is that C0 and C1 are free of k. So I can pull it out. Okay? And now if you lean back, this is exactly my an, and that's exactly an plus 1. So I obtained a linear recurrence. Okay? And using now my g explicitly given here, I get that recurrence relation. By the way, on this level, it's already hard to verify it's correct. So you need the sum and recurrence to verify correctness, and after summing, you might have lost information. Here not, because we have still the a. But if I send now a to infinity, because that, then I get that recurrence, and then it's hopeless to verify that this sum indeed is a solution of Z. So you need the sum and recurrence together with a limit. So if you turn it to a definite thing, it's hard to verify. Finally, I solve the recurrence. Here it's trivial, it's a first order recurrence, variation of the constants. You can immediately read off the solution. Later we see other examples where it's not anymore so obvious. In this case, we find one particular solution, and here the harmonic numbers and the harmonic numbers of second kind pop up. And there is also a homogeneous solution, a solution of the homogeneous version, which is Z. And using one initial value, n equals 1, we finally get that we obtain that simplification. Why is this correct? Well, we know left-hand side and right-hand side both satisfy the same recurrence. Here we used creative telescoping to compute it and to verify. Here it's trivial to verify that this is a solution, plug it in and use again such relations. And then you need one initial value, because then we know both have the same recurrence. They have one initial value, and the sequence is uniquely determined by the recurrence and one initial value. So they must be the same. You can say it's an inductive proof, but it's also by the recurrence in initial value problem, which guarantees left-hand side equals right-hand side. Of course, internally, I use 2 or 3 values because there might be some technical problems and it's safer. But one value would be enough. Okay, here's again the example. I insert the sum. There's another comment, generate recurrence, which produces you the recurrence that you have seen. Then you compute the limit, and I use again the expansion, asymptotic expansions of harmonic sums. I have in comment solve recurrence, which finds you the homogeneous solution. This is indicated by that 0, and the 1 indicates it's a particular solution. And finally, I have a comment find linear combination, where at n equals 1, the sum evaluates to 1/2. This is another round of symbolic summation to get it. It's not obvious. You have to run again the code to get the 1/2. And then you get this closed form. Okay. Here it's basically executed live. I insert the double sum. I compute the recurrence. I perform the limit. I solve the recurrence. And finally, I combine the solutions. Here's a closed form. Okay. So in other words, this very ugly sum here turns out to be that. Okay. Here it's k equals 1. So k equals 0 is another round of summation that I have to add. And in the end, I get that expression. And now you see here n equals 1, 2, 3, 4. I can compute very efficiently and fast. Okay. You know the harmonic numbers of second kind, and you can quickly compute and have you can have also the asymptotic expansion. You can do analytic continuation, which is sometimes used in physics to look how it behaves in complex space. You can do the inverse Mellin transform to go to X space in physics. You have now all the flexibility. Okay, so let's recall the summation tools. The first one was creative telescoping. You are given a definite sum, where the summand can be hypergeometric, like Gosper, but in Zeilberger's version, or it can be an indefinite nested sum and product. I will make this a bit more clear in a minute. It can be, so harmonic numbers can be involved, more general objects can be involved. Then I can try to find a recurrence. It's not always clear that I find a recurrence. It depends on the structure. So if, for instance, harmonic numbers pop up in the denominator, it's not clear that there's a recurrence. One has to try, and they're not existence theorems so far. Other cases, you know immediately the summand actually is holonomic, so you know there's a recurrence. Then there are different tools, and I claim if I have indefinite nested sums, this is a cool tool and very efficient. But there might be also Frederick's toolbox and other ways to do, okay? Okay, so I try to find a recurrence. If I succeed in that, I try to solve the recurrence, and in general, I have a rather strong solver meanwhile. So it's a recurrence of order D. The coefficients A0, A1 up to AD are given, and the right-hand side are given. And they're given in terms of indefinite nested sums and products. So these guys usually are very often just polynomials in N, but the right-hand side very often are indefinite nested sums and products, complicated objects. But they can also here, they might pop up as indefinite nested sums and products. And then we have a toolbox which finds all solutions which can be again given in terms of indefinite nested sums and products. So this is joint work with Sergei Abramov, Manuel Bronstein, Marco Petruschek, and myself, and also enhancements that we do in the moment. And here are just examples, and I cite no literature which comes from the physics side. It might be also interesting for you to see this. They have cool tools also to work with that, which are maybe not so familiar to you. So the harmonic sums, here I just have shown you some examples, and here I computed even the asymptotic expansion of that one. Sending n to infinity, you get the multiple zeta values, okay? More generally, we have here, for instance, geometric products involved. These are called generalized harmonic sums. You might have these broken sums here, like 3k plus 1, 2k plus 1. We call them cyclotomic harmonic sums. Then there are also binomials involved, like 2j over j. So the central binomial coefficients. They also pop up in physics, for instance. But also I saw them in combinatorics already quite often. And there are tools, and more general tools were extra parameters involved, and also, I think this is maybe a more general thing. There might be even Q hypergeometric involved. If there's a Q to N involved here, there might be something like that, and there might be fancy products which do not factor nicely over the rationale, so you have then complex, weird things. You can write it as Pochamas, but then you need algebraic extensions, and they're looking ugly. But all these are indefinite nested sums, and the crucial thing is, you see here, j goes from 1 to k, and there is no k inside here. J goes from 1 to k, no k inside here, here the same, and k goes from 1 to n, and the k is nowhere inside of these products, so they're indefinite nested. And this has a nice flavor because exactly such type of things I can represent in different strings nicely, as you will see soon. Okay, and if I'm successful to compute the recurrence, I can fully solve the recurrence, which is not always clear. If you give me an arbitrary recurrence, I cannot solve it. I don't know. So maybe there are some Liouvillean solutions with interlacing involved, or you find maybe Bessel functions I heard today already, or other functions, PFQs. But if you find a recurrence of order 8, and I cannot factor it further, I don't get information, I have no idea what functions are behind. But if you find sufficiently many solutions, given initial values, I can try to find a linear combination. If I'm successful, I have a closed form. Okay, here's another example to illustrate that. We have here a triple sum. No harmonic numbers involved, just the binomial coefficients, factorials, alternating sign, and then we sum over S, R, and J. And the boundaries are also dependent on each other. So you have to sum in this order now, so you have no flexibility to interchange. So let's look at the inner sum. And I can now, here this is exactly A equals B technology from the 80s, 90s, okay? You can compute a recurrence. You can use, for instance, Marco Petruschek's hyper algorithm to compute hypergeometric solutions. You find linear combinations, and then you find this closed form. Same trick what you have seen before. Okay, so basically the triple sum actually turns out to be a double sum. Okay. So we can replace it. Now I repeat the game. I sum over R from 0 to j plus 1, and j is my next summation variable. So I look for a recurrence in j. I solve the recurrence with respect to j, and I find the linear combinations, and I succeed and get that closed form. If you lean back, you say, okay, this box is smaller than this box, so this is not simplified, right? It's a larger expression. There's also a sum involved, so I didn't get rid of the sum, there's still a sum, but it's a nice sum because it's indefinite nested. So you see here the j, and the j is nowhere inside. Whereas here, the j is here, it's here, it's here, it's here, it's here, it's a definite problem. This is an indefinite nested problem. So I decoupled the thing, I made it simpler. For evaluation, this is good. So I can evaluate this fast. This is hard to evaluate. That's easier to evaluate, okay? But the good thing is, if I plug it back, it's again in my class of objects. The summand is an indefinite nested sum, and I can again compute the recurrence, solve the recurrence, find the linear combination, and in the end, I get this closed form in terms of the harmonic numbers of second kind, and here this s minus 2 means we have the alternating sign in. This is a nice encoding in physics that I like. Minus 2 means there's a sign in the indices. Okay. And that's now definitely a much nicer form. You can evaluate nicely than having that here. So we can run, in addition, now also evaluate multisums and harmonic sums. And this package basically uses these packages, and I encoded all my knowledge. And there are many tactics how you can do it, and I try different versions and look what is the best way to do it. So you just insert the sum, you say evaluate multisum, and then you get the result. So let's do that. So I insert the summand. I insert the sum, and then you do evaluate multisum. It tries telescoping, it tries creative telescoping, it tries to find extensions. So I might find nice sum extensions. So I look in a larger ring to solve something and look for the best way, and voila, after a while I get the result. Of course, this is now a black box, but you can basically check all the steps and you can verify. And I have also verification steps built in. And I did, meanwhile, I think 100,000 such objects. And if I have huge projects in physics, for instance, and there's at one place an error, the whole thing is wrong. So one needs stable software to solve these problems, okay? And I cannot do this by hand. One really has to automatize this, otherwise no way. Okay. Here's another example. I love to show it, and I have to show it once more at least. I got once, this is a long time ago, an email from Doran. In that time, Herb still was alive. He sent it to Robin and Herb. I'm willing to bet that Carsten Schneider's Sigma package for handling sums with harmonic numbers can do it in the jiffy. Carsten, please do it and CC the answer to me. So I got this email in morning, it was a hot summer day. What is this? Doran is doing a bet and I have to do the work. And what is the problem? So actually, I looked at the problem, and it took me in that time quite a while, 1 week to solve the problem. Now it's much faster. And I had to look up the word jiffy. I didn't know that. So it's a diminutive version of a minute, okay? And it was not a minute in that time. But now it's a minute. So let me just show you the problem that Robin Pimenta sent, Herb Doran. I have a sum that when I evaluate it numerically, looks suspiciously like it comes out to exactly 1. Is there a way that I can automatically decide this? The sum may be written many ways, but one is as this. So you see again the harmonic numbers, a two-infinite summation quantifier, and that. And if you do it numerically, it looks like it's 1. But it's embarrassing to write this big sum in a paper. It arose in the bound of the simplex algorithm, and it's 1. Then you should write 1 and not this ugly sum, right? And he was nervous. What is this constant? And well, you start with an inner sum, you compute a recurrence, you solve the recurrence, you have 2 solutions in it, so it's now a recurrence of order 2. I find two solutions of the homogeneous version in the particular solution, same trick. I combine the solutions. It turns out that one is 0. Here is the theta 2. This is the other initial value that enters. And it turns out that sum simplifies to that in terms of theta 2. Now I do the next summation quantifier. In this case, I do telescoping, limit calculations, and I get that value, which is almost 1, but not quite 1. If it were 1, it would be a sensation. We would have a relation between theta 2, theta 3, and theta 5, which would be amazing. So it's not, but nevertheless, yeah, okay. And having that, you can, of course, compute many digits now. It's very easy to compute digits with having that in hand. Okay, and let me show you that it's really a minute or even less. So I insert that, I evaluate it. So I do again recurrence solving, finding linear combinations, and voila. So it's 5 seconds. So I dare to say it's in a jiffy, okay? And here's the result. Okay. Of course, you can play around. You can raise it to the power of 2 and ask what you get. And then we get values in terms of theta 2 and theta 5 and theta 7. Or you have here another version where you raise it to the power in the denominators, the powers. Or you can do triple sums. And you can play around to discover now other identities. Of course, there is a limitation. It has to do with the weight. So here we have a sum of a sum of a sum, and here the denominators. You sum them all up, the exponents and the degrees. You have a certain weight. And then there are multiple theta values behind. And if you go to weight 15 or 16, there are databases available to boil down multiple theta values just to single theta values if possible. But if you're too high, then I can only return these multiple theta values without simplification. And you don't, there may be relations behind, but we don't know them. Okay, that was, yeah?
What did you change so that it was very slow from the clinical Zeilberger problem? First, when you tried it was very slow, and now it is very fast. So what did you change?
In the beginning, I didn't have this automatization. I saw the first time such infinite sums to compute limits, taking care that if you do creative telescoping, the infinite variable only appears on the right-hand side and not in the coefficients. You had to think to make your mind free to understand that this machinery works. It was the first time that I basically used it, and then with this multiple theta values, that there are relations. So originally I looked at the Flageolet paper with Euler sums. With multiple theta values, it's more elegant, and there's a huge database by David Broadhurst, Jos van Maassen, and Johannes Blümlein. They go to this form that did calculations, half a year of calculation, to use all the relations of shuffles, double relation, double shuffle relations. And I think they are all relations that we know, and I think these are all relations that exist. But of course, claiming that this is a polynomial in the variable theta 2, theta 3, theta 5, theta 7, this is far away to proving it, but I believe they are all algebraic independent, but we not even know if theta 3 is transcendental. It's embarrassing, but we all believe, or at least I believe. Or if there's a relation, it's so gigantic that it will not fit into in my notebook at least. So I will never enter this problem to make division by 0 because there is a relation that I don't know. Nevertheless, now I would like to go a little bit to the difference ring setting. So I want that you see a bit difference ring theory before tomorrow I can go into details. Okay, and let's look at the simpler example. I just want to sum the case harmonic numbers. It's easier for looking at the problem. Okay, so I solve the telescoping problem, given the summand being the case harmonic numbers. Try to find a G such that the telescoping equation holds. In this case, we find that solution, the case harmonic numbers minus 1 times the polynomial k. Summing over that by the telescoping trick, we get that closed form. It's just a simpler version of what you have seen in the beginning. Okay? Now, let's start slowly. I design now a difference ring and I do it now by hand and hand waving. It's not automatic. This comes tomorrow, how this works. So let's look at the summand. In all the summation problems that I'm working, I have a field of characteristic 0. So the rational numbers are contained in the field, the starting field as a subfield. Okay, rational numbers are contained. And I try to model the shift behavior by an automorphism. So I take an object and by an automorphism I shift it. Okay? The rational numbers are always fixed. 1 is mapped to 1. This is the definition of a ring homomorphism. And by that, 1 plus 1 must be mapped to 2, and so on. So all integers are mapped to itself. And then by the quotient construction, any rational number must be mapped to itself. There's no way out. So if I define an automorphism, the rational numbers are kept fixed. And that's basically the definition of a constant field or set of constants. If I have a ring, in general, I take basically all elements from this ring such that the elements are kept invariant by the automorphism. Okay? These are the set of constants. And one can show if A is a field, then this will be actually a subfield. And if A is a ring, then this will be a subring. Okay. So, but by definition, the set of constants are just the rational numbers because I define it in this way and there's no other way. Okay. Now let's look at the summand. There is a k involved. So I introduce a new variable. And this, in this case, this is a rational function field. So it's a polynomial ring, and then I do the quotient. So k is transcendental over q. And the automorphism is defined in such a way that I have this shift behavior. If I shift the variable k, it should be k plus 1. So I define the automorphism that k is mapped to k plus 1, and defining it in this way, the automorphism is uniquely determined. There's no other way saying I want this rule and that rule, then the automorphism is uniquely determined because you pull over the elements. Okay, and finally, you see we have here the case harmonic numbers, and the case harmonic numbers in its shifted version can be written like that. It's basically that relation. Okay, I model the shift behavior of the case harmonic numbers. So I introduce a new variable. I could go to the rational function field. This would be a field version. Now I stay in the polynomial ring version. So here we have a variable. Okay, and sigma of h is mapped to h plus 1 over k plus 1. It just models this shift behavior. And it's not obvious anymore that the set of constants are, again, the rational numbers. But the summation theory guarantees us how we do it, that the constants are still the rational numbers. So whenever you find a constant, it's free of h and it's free of k. Now I have basically reformulated the problem. Given the right-hand side, h, find a g in this ring such that this difference equation holds. And now I'm completely on the computer algebra level. I just work with polynomials. I work with formal rings. I make this clear tomorrow. I don't work anymore with sequences which have an infinite representation. So the strength of computer algebra is that you can model something which is infinite to something which is finite and solve some problems there. In this case, I find this polynomial in the variable h and k. And now basically this is hand waving. Tomorrow I make this more precise. Knowing that sigma models the shift behavior of our sequences with the k harmonic numbers, I get basically now also a solution on the sequence level. Okay? But this has to be clearly explained next week. In the moment it's hand waving. From that solution in the computer algebra world, I get a solution on the sequence level. And finally, summing over that, I get that. Okay? Let's go to creative telescoping. I want to do that summation, again, the case harmonic numbers, times n over k, the binomial coefficient. I construct a difference ring, as you have seen earlier. I start with the rational numbers. They're kept fixed. There is a constant n involved. So if I shift with respect to the summation variable k, it's a constant. Okay? So I join a new variable. I say, okay, n is a discrete parameter, but now it's a variable n, which is algebraic independent over q. So it's a rational function field. And these elements are kept fixed, invariant. So not only the rational numbers, but also all elements which depend on n in this field are constants. Okay. Next, I again introduce, we see here the k here and here, so I introduce this shift variable. It's the same construction that you have seen in the previous example. Now we see here the binomial coefficient n choose k. And if you look at the shift behavior, it's hypergeometric. If you shift the binomial coefficient with respect to k, it's the binomial coefficient times this rational function. So this is also the definition of being hypergeometric, that the shift quotient is a rational function. One could also shift in n. I ignore this in the moment, just with respect to k. So I introduce a new variable. And in this case, I could go now to various versions. I could go to the polynomial ring, but I want to be flexible. I go to the ring of Laurent polynomials. Okay, so P is transcendental over this field. So sorry, here it's even over that field. But also I introduce 1 over P. Okay, and P times 1 over P is equal to 1, is the relation. So we have these Laurent polynomials, and this forms a difference ring. So you can uniquely, again, extend the automorphism by saying this map should be satisfied, that you apply it on all of the terms. And finally, we see here the harmonic numbers. So introduce a new variable, and we have this shift behavior. And now in this world, I try to solve the problem. So given the summand, this is just S times P. S, the variable S stands for the harmonic numbers. The variable P stands for n choose k. I try to solve the telescoping problem, and I fail. I cannot find a solution. Okay. Now I do the next. Maybe remember creative telescoping, so I don't find a solution. I now shift with respect to n. Shifting with respect to n, then now I use another relation. If I shift the binomial coefficient with respect to n, we get that factor. Okay?
So if we don't find a solution here, it's a decision procedure. I mean,
It's a decision. There's no solution. There's no solution.
So you have like you can provide something that says
no solution. I will make this also clear next session. So I fail and I don't find. But even if my algorithm fails, and there could be, I could still continue like that. It would be still interesting. So in other story. But then I have a bug in my code and it might pop up somewhere else again. So there's no solution. Okay. So I shift with respect to n, and now observe that this object can be again specified in the ring that I have defined already. The harmonic number stands for S, the binomial coefficient by P, and these elements here are just the elements I can carry over. So I try to find now a G and constants C0, C1, such that this difference equation holds. This is creative telescoping in the ring setting. Okay, and I fail again. So I shift the second time. In the sequence world, I have that. In the ring version, it's that object. And I try to find a linear combination of G and constants C0, C1, C2, such that this difference equation holds. This times I find the solution. You can now plug in. And now I don't have to do hand waving and saying, I have to use this relation. I just apply the automorphism, and then it's polynomial arithmetic. So it's even easier to simplify. Verify correctness. Having that, I can now retranslate that in my sequence expression. So S, the variable S stands for the harmonic numbers. The variable P stands by n over k. So I get the sequence expression. And if you don't trust my code, you can again, on the sequence level, verify on this level. But it's the same as verifying on the difference ring level. Finally, I sum this equation over k from 0 to n. Then on the left-hand side, all terms vanish. And on the right-hand side, we basically get the sum back on this side. Here we have to sum to n plus 1. So I have to subtract one term to make this right. Okay, and here I sum only up to n, but I need to sum up to n plus 2. Okay, so I have to subtract these two terms to verify, to make it fine. Okay, but in this way I can express the right-hand side in terms of an plus 1, and an plus 2.
Excuse me, I have a question there. Maybe you already said it, but how do you have constraints on C0, C1, C2?
Yeah.
Like on the degrees of the numerators,
yeah.
denominators, and so how do you find them?
Yeah. I have to bound.
Okay.
I need bounds to find solutions. This will be also made clear. So in the constant field, that's no problem. This is linear algebra where I can guarantee. But the other levels, I need bounds. I will address a little bit this tomorrow. Okay.
So you need the fact that it should be a field. The constant should be a field.
I want the constants to be a field. I make this in a minute. I make this more clear. A second, one moment. One could work also with rings, but it's harder. But then you have modules, and I want to work in a vector space. Okay. We sum over that, and then we find that recurrence. Okay. Now we have basically done this level. I want to solve the recurrence now, so I'm on this level. And here you look basically for D'Alembertian solutions, and the idea is that I factor the operator. So here you see a recurrence. For simplicity, I just look for the homogeneous version, so the right-hand side is 0. And I write it as an operator. So instead, I have here the shift operator, and acting on n d times is exactly this guy here. Okay. And now one could use, for instance, hyper in this case, by Marko Petkošek, and I find one solution, a hypergeometric solution of the recurrence. Okay. It's like with a polynomial. If you find the solution of a polynomial, you can factor off. Okay. You can factor off this factor, and you get basically an operator of one order less. And now I repeat this. I apply hyper on that level. I find if I'm successful. If I fail, I have to stop. If I succeed, I find another solution, and I can factor further. I find another factor. And if I'm lucky, I can do this d times. Then I have fully factorized the operator into linear factors. And this is now a generalization of variation of the constants. This factor here gives me the solution that you have here. This was the starting point, okay? But the second solution is a sum over that hypergeometric product times B1, the B1 factor. So we get another solution. And we can do this d times. And the solutions are linearly independent. So over the set of constants, the constants. If you are on the fields, they are linearly independent. And that's the crucial thing. If you have a big recurrence and you solve it, you find huge solutions, highly nested. Let me show you an example. Okay. An example here. This is a recurrence coming from physics, and it's a simple recurrence. Okay. Here it's a shifted 3, 4, 5, 6. A recurrence of order 7, degree 60. So later you will see recurrences of order 60. The degree is 1,000, and the digits needs maybe 10,000. And if you want to print it, you need 20,000 pages, for instance. Okay, huge recurrences. Now I solve the recurrence, and I factor it. So here you see the factorization process. Okay, and here are the solutions. One is a solution. Then you see here a simple sum, another sum, a sum. They're single sums because I find simultaneously 3 solutions, so I don't have to make this nestedness. But in the next sum will be already a 5-nested sum. And you see the denominators do not factor nicely. They are ugly denominators. Of course, you could factor over the complex numbers, but I don't want, in a computer algebra system, working with such extensions is horrible. So get rid of these denominators if possible. And these are the solutions. The solutions are as bad as the recurrence, similar size, okay? But the solutions are indefinite nested, so I can use my telescoping tricks, and I will explain this in more details tomorrow, what one can do. I factor again, this goes so fast, I repeat. And afterwards I do simplifications. These are the sums that pop up. Each sum I do telescoping, and I build automatically a difference ring to represent it in an optimal way. I have to make this clear next week how this, you cannot do this, let's introduce a variable in the variable, you have to do this automatically, okay? And you have to do it in the right way. But after doing so, we have set solutions. Of course, the one solution I haven't simplified, okay? The next solution is other harmonic numbers of third kind. This here you could use Abramov's algorithm of the 70s, 80s, or 80s. But you see it gets more and more involved. And maybe the most complicated object is something like that. Okay? There are no bad denominators anymore. These huge denominators are gone. The objects are flattened. It's only a 2-nested sum, not a 7-nested sum. And I've simplified it. And using 7 initial values, you get that expression, which fits on one page. So, and by the way, this was a minimal recurrence. If you take this and guess the recurrence, you will get the previous ones. So the recurrence representation is awful. The nested sum representation is wonderful. And we have asymptotic expansions. We have full control about it. Okay. So let me say the message. The constructions are highly nested because we factor if I succeed, but then I get very ugly sums. So indefinite summation is an important tool. For me, solving a recurrence, the recurrence finding the solutions is good, it's important, but the simplification afterwards of the solutions is equally important because what should I do with these nasty solutions? Then I prefer to work with the recurrence than with this. So I need a simplification.
The factorization is hard too, right?
It can be hard, but I claim there are tools, but working on the simplification is equally important afterwards. But it's hard here, it's exponential. So here basically now we compute we have the sum, we compute the recurrence, we solve it, and we find linear combinations. This was the end of the story. And let me conclude in the last 2-3 minutes. Here is a general problem that basically I'm interested in. We start with a difference field, first in the field. Then here's a typical field. In this case, we start with x, shift of x is x plus 1, which models basically our summation objects. And h should be s here. In our previous examples, S was a polynomial ring. Now I go to the rational function field because I want the field version. Okay? So the set of constants is defined exactly in that way, as I have shown here. And the crucial thing is these constants remain unchanged after extending x and s. This means the constants of this difference field are just the rational numbers. This is also called the pi sigma field due to Michael Carr from 81. One could work with Carr. I prefer to work with rings, but I will make this clearer tomorrow. Okay? And basically, given such a difference field, I haven't explained how to get it, but suppose we have it in hand. Given f in such a field, find g in this field such that the telescoping problem holds. This was one of the problems that you have seen. I want the telescoping problem in this setting. More generally, I can introduce parameters f1 up to fd, find all g and all constants such that such a parameterized telescoping problem holds. And you have seen this problem. This is exactly this problem here. Find g and all constants such that this holds. This was I can use for creative telescoping, but it's more flexible. The f1, f2, f3, they don't have to be shifted in n. They can be any element. Okay? Different applications. You can look for contiguous relations, for instance, following Gauss, but in a more general setting. There's more flexibility here. Okay. And well, even more general, we have also introduced a0 up to m from this field, not the zero vector. Then one can look for parameterized linear difference equations, which I'm interested in. This is, for instance, also used in the holonomic approach to solve this problem if you're in the rational functions. And well, if you look now, what does it mean? I want to find all solutions means give me all vectors, g, c1, c2 up to cd, okay, such that this holds. And one can easily show it's a k-subspace of Z, and the dimension is bounded by d plus n. So the number of parameters and the order of the recurrence. Okay? This is a differential equation of order d, has at most d solutions over a field. And for a recurrence, it's the same. If a recurrence of order d, there are at most m solutions, linearly independent, over a field. And the parameters d naturally go in. And I want to find basically a basis of Z. That's the main goal. Okay? And maybe an appropriate extension, like these Liouvillean solutions or D'Alembertian solutions, find a bigger ring, such as find the solutions. And this is interesting for telescoping, this is interesting for creative telescoping, that you find extra solutions or something like that. And here's an example. Here's a recurrence of order n plus 1, n plus 2, and the coefficients depend on the harmonic number. So I'm working now in the field world of a very general field where the harmonic numbers are in my field. And I find here now hypergeometric solutions over the harmonic numbers. So this is a generalized version of hyper, which is exactly this work that I did with Marco and Michael, Manuel Bernstein, and Marco Petruschek. And here's another example where in the coefficients you find the n factorials. Then I find here the D'Alembertian solutions, a product of a product. So hypergeometric over the factorials. I would love to see applications. I haven't found. It's maybe a bit exotic. It's cool to do it, but I would love to see applications. So if you know some, tell me. Okay? And we heard field ring. We can also go to a difference ring. Here I will take care that the set of constants is a ring, not anymore a field, but during the construction I will take care that it's always a field. I start with a field because the sequences evaluate to a field, and then when I extend, I take care that the constants never leave the field version. Okay? One has to be careful with the dimension. In the ring setting, if you have 0 devices in the leading coefficient or in the trailing coefficient, this is subtle. But we have also tools here, and this is work in progress. For instance, here you see a recurrence of order 2, inhomogeneous, and you see also the alternating sign involved, -1 to the n. And here we get 0 devices. Trust. And see if we have 1 -1 to n times 1 plus -1 to n. This is 0. Okay. This is 1 minus -1 to the n squared. And -1 to the n squared is 1, so you have 1 minus 1, this is 0. So these are 0 devices. So this is the sequence 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and this is 1, 0, 1, 0, 1, 0. If you multiply, you get 0, 0, 0, 0. Okay? You might have 0 devices. This is a problem. But this is a work in progress of a current PhD student in our Eagles project, and he made cool extensions that this works also automatically here. Okay, so this was a summary of my talk. We have this circle to go creative telescoping, recurrence finding, indefinite summation, combining the solutions. And next week, I want to go into more details about the difference ring theory, how we can automatically construct such a difference ring that it works, and extract nice properties like the transcendence of such summation objects that I represent. So this will be next week. And then the last part will be then dealing with applications. Thanks.
Thank you. So I already see a question, so I will give you the mic.
Hi. So actually I have 2 questions that may be related. So the first is that somehow beyond the extensions with n and k, you seem to be hesitant whether you will take ring or field difference extensions. So do you have a rationale to tell what you want? And related to this may be related. One of their examples introduced p and p minus 1, which I understand to be binomials, or to represent the binomial sequence. What does it mean, or how will you interpret your result, knowing that p minus 1, which is the inverse of the binomial, is 0 almost everywhere?
Sorry, 1 over p.
1 over p, I understand,
P
is
is
one
is a binomial coefficient.
Yes, so 1 over
zero.
binomial nk is 0 almost always. That is when k is not between 0 and n. So how do you, why did you introduce p minus 1 in the first place? What made you decide to do so, knowing that there will be the problem afterwards?
So that are two stories. So the first thing is, why do I use rings and when do I use field version? So of course, if the harmonic numbers are in the denominator, I have to model them somehow in the denominator, right? If I'm lucky, I can do that by a kind of quotient ring construction. One has to be careful. If I have already designed a ring, then I can do a quotient ring construction to do that. So my main motivation is, one could go directly to Carr's world as much as possible in the field version, but then I have denominators where I don't know if I evaluate them, if they're infinitely many times 0 or not. And I have a big problem to handle this. I don't know how to do it. I think if you have nested sums and products and sums and products, it's very difficult to say and I not only want to say it's only finitely many times 0, but I want also the point from which point on it's not anymore 0. Because I have to deal with that. Otherwise, I cannot represent sums and products as a sequence. So with 1 over p, yes, you're right, but I define it in the shift operator, and there I don't have 0. So I have to be very careful with the evaluation later to interpret it again properly. But on the ring level, I don't have zeros. And because if I know the binomial coefficient, I know it's from a certain point on there is no 0 anymore. So if I take 1 over the binomial, I know also that it doesn't have zeros from a certain point on. So I have full control about the Laurent polynomial ring. If I go to the rational function field, and there are binomials in the numerator, denominator, all over in the place, I don't have control from which point on something is 0 or not 0. That's my main problem. If this is solved, I could go to much more general settings. But I have to go to the ring version because I have also such 0 devices, and this cannot be handled in a field. I could, but then I introduce the constants and I don't model the object anymore. So minus 1 to the n squared should be 1. This is, otherwise you lose information and then you get larger recurrences if you do creative telescoping. Yeah, there's another question.
Do we have any sense of the complexity of solving for G? Like just
No.
we take any...
I haven't done that. One could, so one can reduce it to linear algebra. For certain problems, one certainly could do complexity analysis, but I haven't done this. I wanted to have it fast and it should work, and if it works, I don't ask the theory behind it. But,
Thanks.
But it's an interesting question, definitely.
So now it's time for a coffee break, so let's thank the speaker again.